Hi everyone. In today's session, we shall discuss second part of our unit 4, torsion. So, in this session, I would like to discuss what do you mean by torsion and the derivation for torsional equations like the bending moment equations, which we studied our in unit 3, and torsional moment in solid and hollow shaft, and power transmitted by the shaft. So, first, what do you mean by torque? A torque is nothing but a twisting moment or a couple, and it is also called as star, which tend to rotate the plane perpendicular to the longitudinal axis. So, like this is nothing but torsion, or the twisting moment is also called as a torque or a torsion. So, these will be generally we can see in cylindrical sections of solid or a hollow, which may be of a steel or a copper alloys, and these are subjected to following the loads. One is only torsion load, and torsion with axial loads, and torsion with bearing, bending and transverse loads, and also with axial and bending loads. So if you see this, before the transformation, the positions of P and Q are like this. After applying the twisting moments, the positions are changed to P dash and Q dash. So before deriving the torsional equations, there are few assumptions to be followed. The first, the material should be uniform and the shaft should be in the circular section even after the loading also, and the plane section should be normal to the axis and remains plane. The torque has to be applied, and the twist along the length of the shaft should be uniform. The distance of any two normal sections same even after removal of the torque, and the maximum shear stress induced in the shaft is due to torque does not exceed to the elastic limit value. So these are the assumptions while deriving for the torsional equation. So now let us consider a torsion for a solid shaft at the PR positions. Okay. Let us consider the length of the shaft as L, radius as R, and the polar momentum inertia of as J. And we are assuming the maximum shear stress is assumed to be tau of S, and modulus of rigidity, which is nothing but shear stress by shear strain, that is G. And the shear strain assumed in the shaft is gamma S, and the angle of twist is phi. So a shaft is fixed with a portion, and in the line PQ, if you are applying the torque with the angle of twist R phi, the surface angle is phi. So here the position will be changing from Q to Q dash. So the Q dash by L is equal to some angle with respect to radius of angle R phi by L. So this is your shear stress, and we know that modulus of rigidity is shear stress by shear strain. So which is from Hicks law. So tau S by G is equal to R phi by L. So let this be equation 1. So now consider an elementary ring of thickness dx and the radius of for shear stress R. So the area of the turning force will be 2 pi dx into tau x, and the turning moment will be the product of its distance. So 2 pi x square dx into tau x. So on integrating this for a small force, tau is equal to with respect to radius, so 0 to pi, 0 to r, 2 pi x square dx into tau x. So 2 pi tau x by r is constant, so we can remit by itself. So x square into x means x cube. So the derivative of x with respect to x cube is x power 4 by 4. So if I substitute the upper limit and the lower limit, so r by 4, r power 4 by 4. So on simplification, I can write it as tau s into tau by r into j. So t by j is equal to tau s by r. In this first equation, I got ts by r is equal to g5 by l. So on clubbing these two equations, I can write it as t by j is equal to tau s by r is equal to g5 by l. So this is called our torsional equation. Based upon this equation only, we'll be finding the power of the shaft, and when the series when the shafts are in series or a parallel, and many problems can be identified. So now how the torsional moments of will be varying for solid and hollow section. So now let us consider a solid section of solid shaft with a torque subjected to T, and the radius is R, and the diameter of shaft is D, and the tau s is shear stress due to radius. We know that the torque is 2 pi x into dx into tau x. So on substituting on integrating the above equations, so I got it as 2 pi x square tau of x into rx dx. So pi into tau s r square by 2. So tau s is nothing but pi ts r cube. So if I take in terms of radius, in terms of diameter, d by r is equal. So pi into tau s d cube by 16. Similarly, it will be the boundary conditions will be varying for hollow sections. Am I right? Why? Because for solid section we will be having only one diameter. For the hollow sections we will be having inner and outer radius. So with respect to the radiuses of r and r, if I derive to the torsional element in the ring, so I got it as pi tau s d power 4 by d power 4 minus small d power 4 by 16d. So this will be the torsional equations for a solid and a hollow circular shaft. So now we shall discuss about how much power produced by the shaft. So let us suppose a force of F is Newton acting on the shaft and the radius R. The torque is equal to force into perpendicular distance. So tau is equal to F into R. The power transmitted is T mean into angular speed. So torque mean into angular speed 2 pi n by 60. So from the torsional equation, T by J is equal to G5 by L. So angle of twist will be tau L by Gg and the torque can be Gi by L into phi. So where GL I by L is termed as K, so therefore torque is equal to K phi. So this is the torsional power shaft, power transmitted by the shaft using torsion. Okay. So now let us solve one problem. A shaft is made from tube. The ratio of inner and outer diameters are 0.6. The material does not experience shear stress greater than 500 kilopascals. The shaft must transmit 1.5 megawatts power at 1500 revolutions per minute. Calculate the shaft diameter. So since it is a hollow shaft, we should be finding the outer radius and inner radius. And he has given the power as 1.5 into 10 power 6 watts and the torque as 500 into 10 cube kilopascal, so 10 power cube pascals, and the revolutions as 1500 revolutions per minute, that is RPM, and capital D is 0.6 times of small d. So we know that power is equal to 2 pi nt by 60. From that I can get the torque P by 2 pi n. So I got it as 9549.3 Newton meter. And we know that J is polar moment of inertia, that is pi by 32, capital D power 4 minus small d power 4 by 32. And the ratio I got it as 0.00854. So I know the equation, torsional moment equation, T by J is equal to tau by R. On simplifying, I got the capital D as 481.6 mm and small d is 0.6 times of capital D. So 289 mm. So these are the some short and essay answers asked in your previous question papers. Thank you.